Okay, so in this video, I want us to explore some alternative invariants, ones that we can maintain that will help us reach this final goal of making contains key have a worst case runtime that's more efficient than big theta of n. So we're going to consider a few different invariants, and I'll explain them in just one second, kind of where they're coming from. But what I want us to do for each one is I want us to consider, does this invariant help us? Is it strong enough to make sure that contains key is going to be efficient? And maybe on the flip side, is it potentially too strong that it's so restrictive that it's going to be really hard for us to meet it? And so for each one, I'm going to have us try to come up with an example binary search tree to maybe show as an example whether or not it's strong or not strong enough. And we're going to use this exercise as a way of trying to understand what makes an invariant for these binary search trees useful, and to get a hint at how we might come up with the solution that we'll see in a little bit for this thing called an ADL tree. So here are three invariants I want us to consider. The first one is what I'm going to call root balanced. The idea for the root balanced one is that the overall root node at the top must have the same number of nodes in both its left and right subtrees. So that if that's true, then we're going to call it root balanced. Another one I want us to consider is one that we're going to call recursively balanced, which is kind of an extension of the root balance case. But instead of only applying to the topmost node, we're going to make it apply to every single node of the tree. So every single node in the tree must have the same number of nodes in its left and its right subtrees. And then this third one we're going to consider is this one that I'm going to call root height balanced. It's very similar to the root balanced, but instead of counting the number of nodes, we're going to count the height of the trees. So the left and right subtrees have to have the same height when we're looking at that overall root, the top node. So let's dive into these and see, will any of these invariants kind of help us reach the solution of maintaining a short binary search tree? So let's start with the root balance case. The root must have the same number of nodes in its left and right subtrees. So take a second, we'll pause, and do we think this invariant is going to work? Is it strong enough to make contains key efficient, or maybe is it too strong? It'll be too restrictive for us. What might go wrong here? Take a second and tell us what you think. Okay, so I would argue to us here that this invariant is going to be ending up to be too weak, meaning that even if we meet this invariant, it's not going to help us reach our goal of keeping the tree short. Let me show you an example tree where something like this can go wrong. So remember, here we just need to make sure that with the overall root, that its left and right subtrees have the same number of nodes. Let me draw a little tree here. Let me try drawing a tree like this. There we go. A tree where its left subtree has 3 nodes in it, and its right subtree also has 3 nodes in it. Bear with me with the drawing skills. I'm using my little trackpad here. You can imagine that these nodes can go on for a long, long ways. Essentially what I've just done here is I've just recreated our degenerate tree, and I've made 2 degenerate trees that are the child of this overall root. And you can make these such that both the left and right subtree have the same number of nodes, but that worst case runtime, if you're searching for a key, you might still have to go down all the way down one of the chains. So you're going to have something like n over 2 worst case runtime whenever you're searching for a key that might not be present, right? Half the nodes, because we know that there's going to be the same number in the left and right subtree, half the nodes are going to be in one side. So we're going to eliminate half of them. But then once we're in that second subtree, well, then we just have to search down this essentially linked list. So it's really not going to actually make this asymptotically better than big theta of n. So let's try another one. Let's try the recursively balanced invariant, where now this is a slightly stronger statement, but now every node, this balance of left and right subtree having the same number of nodes applies to every node, not just the root node. So take a second, what do we think about this one? Okay, so this one's a little bit trickier. This does seem to solve the problem a little bit in the sense that you can't have those degenerate children because then they won't be balanced, right? This property wouldn't apply to them. But what I'm going to argue to you is that this invariant is going to be too strong. If we try to meet this invariant, we're going to have a really hard time building up a tree. So and this always works with examples. So thinking about examples of where this works or where this might not work. This is much better on the right idea, but it's going to end up being a little too tough for us to meet. So consider this tree. Press these buttons. It's always the weirdest sequence of key commands I have to press to get this drawing to start working. So consider a perfectly complete tree. So we have some nodes here and some nodes here. So let's just say we have 7 nodes in this tree. Okay. Does this tree meet this invariant? Yes. Every node has the same number of children in their subtrees, or the same number of descendants in their subtrees. So this is okay. But now imagine I want to add a new node to my tree. So imagine I want to add a new node. It doesn't really matter where it goes, but let's just say, for example, it goes down here. Now, this is going to now violate our invariant because that child node, this node here, now has one child on the right and not the left. What I would argue here is that at this point, it's going to be impossible for us to ensure that this balance will happen. This statement is just too strong to actually let us build up trees of any height, because we are going to be limited by our ability to add nodes that are like in odd numbers. That are even, and sometimes in even numbers. It's kind of tricky. But I will tell you that this is starting to get the righter track. The fact that we need to kind of enforce things kind of globally across the tree, like at every level, not just the overall root. Let's consider this one last invariant, the root height balance case, where the subtrees of the overall root have to have the same height. Not the same number of nodes, but the same height. Take a second to think about this. Is this invariant strong, too strong, or not strong enough? Okay, so this one's a lot trickier. In some sense, it seems like it could go potentially either way. What I'll argue is that this invariant is going to end up being too weak. Now, the reason it's going to be ending up too weak is because we can just use that V example again, where we have just 2 degenerate trees as our children of overall root. They could have the same height, but we're still going to have that kind of worst case runtime. Now, there is a very subtle point here that you might wonder, well, wait, couldn't this potentially be too strong? Because, like our last example, it's going to prevent you from adding nodes. However, I would argue here, you could rearrange the tree in such a way that the tree would always have balanced height with respect to that overall root. But it's not going to guarantee us, like balanced height, meaning that the left and right subtrees have the same height. But it's not going to guarantee us that it's going to have this nice overall balanced logarithmic height. However, this exercise, even though we didn't come up with any invariants that ended up working, I think this is a useful exercise to understand what aspects of the invariants helped us and what aspects hurt us. So the first was kind of realizing what I kind of said earlier, is that we need a requirement everywhere, not just at the overall root. And in some sense, this makes sense. If you only restrict to a constant number of nodes, it's not going to help us with asymptotic runtime when our tree gets larger and larger, right? Because in some sense, you could just always tack on degenerate trees at the bottom if we only make rules for the first couple nodes. So this is going to kind of inspire us to think about something a little bit more like that recursively balanced one, where at every level, our invariant was met. But we saw with that recursively balanced invariant that we ran into a problem where if we force things to be exactly equal, it tends to be too difficult to maintain. The reason was, well, there are kind of in-between cases, right? When we had that recursively balanced tree, we had this in-between case where we wanted to add one node, and it wasn't like 2 imbalanced, it was just like it was an odd number of nodes there, or an even number, I guess. But it wasn't going to break anything. That was like as well as we could do with the number of nodes that we had. And so this exact requirement, saying that the left and right had to be exactly equal, is going to be a sign that our invariant might be too hard. And so the idea of what we're going to do is we're going to allow a little bit of wiggle room, some constant amount of wiggle room. And the idea of why this is going to help us is just like before when we want to ignore some constant factors, allowing just a constant amount of wiggle room is going to be okay. It will disappear in our asymptotic analysis. So that's going to be our intuition for just allowing a little deviation from perfectly balanced. And because that'll just be a constant difference, it'll end up disappearing. And these two things combined give us the AVL invariant. The AVL invariant is kind of the way that we're going to talk about making these trees that are able to balance themselves. This is the invariant that we are going to be able to enforce that will give us this logarithmic height. So I have this little spinny icon around to show you that this is the big deal. It will never stop. So if you just want to watch this animation for a while, you can look at the PowerPoint. It's pretty fun. So here's what the AVL invariant means. For every node, the height of its left and right subtrees may only differ by at most 1. So this is similar to the recursively balanced case, except instead of saying the same number of nodes, we're saying that the heights have to be close, and we're not saying they have to be exactly equal. They're allowed to be off by at most 1. So this allows a little bit of wiggle room here. So the AVL invariant lets us talk about these things called ADL trees. So an ADL tree is a binary search tree that also maintains this AVL invariant. It's named after some computer scientists, Adelson, Belsky, and Landis. I can always remember this as a very lovable tree, AVL, a very lovable. And this invariant is very, very clever in the sense that this invariant is kind of just the right sweet spot where it applies everywhere, but allowing that little bit of wiggle room to make sure that it's not too strong that we can't possibly meet it. Now, what I can't argue to right now, and so you're just going to have to kind of believe me on this, is if this invariant holds for every node in the tree, then its height will be at most big theta log n. That if your invariant holds here, then your tree will have logarithmic height, which is fantastic news because limiting the height avoids that theta of n worst case runtime. So this is kind of exactly what we wanted here. Now, the question is, how easy is it to maintain this invariant? So we're going to need a way to talk about how we actually implement our code, like inserting a value into the tree, such that this invariant is maintained. But we're not going to get there quite yet. We'll talk about that in the next video. But I want to tell you that it is going to be a little complicated, but actually kind of straightforward operation that we can do. It's not like how you'd figure out that's the operation you want is not clear at all. But in the grand scheme of things, ends up being a little simple, and it kind of surprisingly works in making sure that it preserves this invariant across the whole tree, which is really, really cool. But we're not going to focus on how to maintain this invariant quite yet. What we're going to focus on now is just making sure we understand what this invariant is asking us. So let's try testing our understanding on a couple trees here. So is this tree here an AVL tree? So take a second and think about this. Yes or no, is this tree an AVL tree? And why or why not? Okay, so this one I made a little tricky on purpose. This one's kind of a trick question. Now, this is not an AVL tree because it doesn't abide by the binary search tree invariant. So remember I said an AVL tree is a binary search tree that also meets this extra AVL invariant. Since we don't meet the binary search invariant, it's not going to be an AVL tree. So we violated the BST invariant. So all AVL trees have to be binary search trees. The reason is the way that we define how to fix this and make sure this invariant holds, it really cares about the sorted order here of binary search property. So it really only makes sense in that context. So now let me give you one that's less of a trick. So is this binary search tree, or is this tree an AVL tree? Okay, so this one turns out to not be an AVL tree. And the reason is it violates the AVL property. There is a node in this tree where it's this node with the 3 right here. Its left child has height, its left subtree is height 2, and its right subtree is height 0. There's nothing there. And since these differ by more than 1, then we say we violated the AVL invariant here. Okay? So now, Let's try one more. Is this one a valid ADL tree? Okay. So you might see that this one is going to be an ADL tree, even though, that 3 nodes still is looking a little sus there with kind of those tall children. If you verify the heights of all of their subtrees, they don't differ by more than 1. So this is going to meet our kind of definition here of balanced in the ADL sense. So hopefully this makes a little bit more sense, kind of how this strikes balance. Notice, for example, if you added another node like 0, but below if you added another node or more nodes down below the 1, then you'd suddenly trigger this imbalance where the ADL definition no longer holds. So this is how it's going to kind of maintain, or how we track it with this invariant. So we'll talk about in 1 second how to make sure this invariant stays, but that will be in our next video.